So this video is going to be a very quick introduction to the InStep Studio's reverse engineering set of tools. Each of these individual items will be covered in its separate video. So this one is really just meant to very quickly go over what the capabilities are roughly and kind of how they could be applied so that people that then want to look at a specific tutorial know which one to take a look at. So let's go ahead and import a file that's essentially feature based. So what I'm going to pick here is just a very simple geometry that's intended to show some of the basic geometric features that can be reverse engineered on a features basis. So there's different aspects to reverse engineering, and this video will cover them briefly, and then each of them will be covered in more detail separately. So importing and going to reverse engineering directly, assuming there's no edits that need to be done, no repairs, and no changes to the body data. In this case, this is clearly very feature based. This is one of the test files that was used during development, and the idea is that we can detect certain types of features. So here there's conical sections, there's cylindrical sections, spherical, and similar. We do that by first defining boundaries, and there's an automatic way to find boundaries. Once the boundaries are found, we can directly go in and define surfaces in between. We can do that using an automatic tool that searches between the boundaries, finds them, identifies them, and colors them according to what shape they are, so that the user has a feedback in terms of what's being found. We can also go in and edit those if the type doesn't match or we want to use a different type, and then once we're done with that, we can apply it and turn that into the actual data that we want to export. This is a case of a geometric feature, and this really only works if the original data is very clearly defined as some polygon style CAD tools do. So applications that don't export to step file because inherently they use a polygon style geometry, these could export to a style like this that can then be further exported to step. An example might be PCB applications where individual components are defined by a set of triangles. So this is a feature-based reverse engineering, and it really only works in very clean and well-defined geometries. If instead we have something that's more organic, so very smooth surfaces, scan data or similar, this is an example that was provided called the upset lady or bust of a female. Here we see there's nothing that's geometric in nature. Even the pedestal itself has a lot of fine details, and if you've seen enough of these, you can recognize scan data when you see it. So this is a scanned object, and it's very difficult to reverse engineer this into a feature base. So for this we have organic shape options, and there's two tools. We're going to cover the manual option in more detail in a separate video, but for an organic shape like this, we may want to just use a rough set of seed surfaces that the tool can automatically generate, that are then overlaid over the geometry, that define a set of patches which we can use in reverse engineering the shape from it, and then export it as a set of NURB surfaces. And NURB surfaces are just surfaces that have a smooth transition from one side to the other. Now this itself wouldn't be a great export. There's some issues here, and we'll cover a lot of that in its separate tutorial. But this would be the case of a geometric conversion from an organic shape. Another option is if we have something that's clearly defined as a geometric shape, but inherently we're not interested in the details of it. So here we have a gear outline, and yes, we could use the reverse engineering with the feature base to try and get all these shapes back, but ultimately that's not what a user is likely interested in. In this case, the most appropriate way of doing this is actually slicing the data, and we can define a plane through the data that acts as an intersection, and then that shape becomes the source of a set of lines that we can use in a CAD program to recreate the solid body by means of looking at the individual segments that make out the perimeter. So in this case, we would go ahead and we would export this as a DXF, and then in the CAD application we bring that in and extrude it into a solid body. So that's be a case where we'd use a slice of a shape. Lastly, we have relief data. So for example, one that we can bring in here would be a relief of data which is defined as being very thin in 2 dimensions but having some thickness in a third. So in this case we can go to reverse engineering, define our parameters, and then generate a preview of what that data would look like as a solid body, extruded in thickness, sampled at regular intervals, and with an underlying shape that's defined through a certain thickness. If we like that, we can leave that as is and export it directly to a NURBS-based model. So these different options are used in different scenarios, and it's really up to the user to figure out what the data is that they've imported and how they want to use it. So in following tutorials we're going to cover each individual ones of these approaches in more detail so that we can dive into the specifics of using them.